Hello viewers, in today's session we are going to discuss an important and conceptual problem from definite integrals. And here we are given this problem where we have to make use of properties of definite integrals, right? So let us first read out this problem. And here we have the problem: consider a function f of x such that f of x plus f of 2 pi minus x is equal to pi square over 4 for all values of x belonging to the set of real numbers. Then we have to find out the value of this integral, that is 0 to 2 pi f of x sine square x dx. So now let us first take this integral as I. So here we'll assume I is equal to the integral 0 to 2 pi f of x sine square x and dx. Now let us make use of this property of definite integral, that is 0 to a, and we have say f of t dt is equal to 0 to a f of a minus t dt. So this is an important property of definite integrals which can be utilized in this integral, right? Because this property is a particular case of this one, that is a to b f of t dt is equal to a to b f of a plus b minus t and dt, right? So let us call this integral as integral number 1, and let us apply this property to this one. So here the value of a is 2 pi, right? And for f of t, here we have this function, that is f of x sine square x. So let us replace all these x by 2 pi minus x due to this property, right? So we have now I is equal to 0 to 2 pi, then we have f of 2 pi minus x, and then we have sine square, and here we have 2 pi minus x dx, right? Okay, now let us take some help from trigonometry. Now see, here we have sine 2 pi minus x, and from trigonometry we know that sine 2 pi minus x is given by minus sine x, so that the square of 2 sine square 2 pi minus x is given by minus sine x square, and that is positive sine square x. So here we can replace this term by sine square x. So we have now I is equal to 0 to 2 pi and f of 2 pi minus x, and here we have sine square x dx. So let us call this integral as integral 2. So now let us add 1 and 2. So adding 1 and 2 will get I plus I in the left hand side, and in the right hand side we have 0 to 2 pi f of x sine square x dx plus integral 0 to 2 pi, and here we have f of 2 pi minus x, and here we have sine square x dx. So I plus I is 2i, and here we can see that in both the integrals the limits of integration are same, right? And here we have sine square x, and here we have sine square x. So we can now write 0 to 2 pi, and we can take f of x plus f of 2 pi minus x, and then here we can take sine square x common, so we have sine square x dx. Now see, we are given in the problem that is f of x plus f of 2 pi minus x is equal to pi square over 4. So let us replace this quantity by pi square over 4. So we have 2i 0 to 2 pi, and here we have pi square over 4 and sine square x dx, right? So let us rearrange the terms. So here we have pi square, and here we have 4 times 2, that is 8, and then we have 0 to 2 pi and sine square x and dx. So now we have to evaluate this integral, right? So in order to evaluate this integral, let us make use of trigonometry, and we know that sine square x is given by 1 minus cos 2x over 2, right? So from the double angle formula for cosine function, we have this result. So we have pi square over 8, 0 to 2 pi, and here we have 1 minus cos 2x over 2, and here we have dx. So this is pi square. Taking this 2 outside the integral, we have 16, and 0 to 2 pi and 1 minus cos 2x and dx. So now we can easily integrate 1 minus cos 2x. So we have here pi square over 16, and the integral dx is x. So here we have x, and the integral of cos 2x is sine 2x divided by 2, and the limits are from 0 to 2 pi. So now let us substitute the limits, and we'll take the difference. So when x is 2 pi, we have 2 pi minus sine 4 pi. Here we take x is equal to 2 pi, and here we have 2, and then we have 0 minus sine 0 over 2. So this is pi square over 16. This is 2 pi, sine 4 pi is 0, and here we have 0 minus 0, because sine 0 is 0, and sine 4 pi is also equal to 0, because we know sine n pi is equal to 0 for n any integer, right? Okay, so here we have pi square over 16, and here we are left with only 2 pi, right? So this is pi square times pi is pi cube, and here we have 8, right? So the value of this integral, that is I, is equal to pi cube over 8, which can also be written as pi over 2 whole cube. So viewers, this is how, by the application of the properties of definite integrals and some concepts from trigonometry, we can easily solve these kind of problems. Hello viewers, in today's session we are going to discuss an important and conceptual problem from definite integrals involving the modulus function. So here we have to evaluate this definite integral where the limits are from 0 to half, and the integrand is a mod function, right? So here we have a mod of x times cosine pi x dx, and we'll solve this definite integral using three important concepts, including the method of substitution in integration, right? So let us first quickly see the three important concepts which are going to be quite useful in evaluating this integral. So let us first call this integral as I, right? And here we have the three important concepts which are going to be useful in the evaluation of this definite integral. So the first one is a definition of mod function. The second one is the sign convention for cos theta in 4 quadrants, and then the third one is integration by parts, right? So in the first case, we have the definition of mod function. See, the mod function is defined as mod of p is given by a positive p whenever this p is greater than 0, and mod of p is equal to 0 when p is equal to 0, and mod of p is equal to negative p when p is less than 0. So this is the definition of mod function, right? And the second one is the sign convention for cosine function in four quadrants. Now see, when we have the four quadrants, here we have 0, here we have pi by 2, then we have pi, then we have 3 pi by 2, and here we have 2 pi. Now we know that from trigonometry that the cosine function is positive in the first quadrant and in the fourth quadrant, right? And in the second and third quadrant, the cosine function is negative, right? So from 0 to pi by 2 the cosine function is positive, and from 3 pi by 2 to 2 pi the cosine function is positive, and from pi by 2 to pi the cosine function is negative, and again from pi by 2 to 3 pi by 2 the cosine function is negative, right? And the third one is the integration by parts. Now see, we know that the integration by parts formula goes like this. If we have two functions, say u and v, and the integral u dv is given by uv minus, then we have v du, right? So this is the formula for integration by parts, where u and v are some functions of x, right? Okay, so now let us first apply the method of substitution. So here we have cos pi x. So let us first take t is equal to pi x, right? So that x is equal to t over pi, right? And here we can see that the value of x, it varies from 0 to half, right? Okay, now let us differentiate x with respect to t. So we have dx over dt is equal to d by dt of t over pi, and we can take 1 over pi outside this operator. So we have d by dt of t, and the derivative of t with respect to t is 1. So we have 1 over pi times 1, that is 1 over pi, right? So now we can write dx is equal to dt over pi. So now let us change the limits. See, here x varies from 0 to half. So when x is 0, then the value of t can be calculated from this substitution. T is equal to pi x. So we have pi times 0, that is simply 0. And when x is half, then t is given by pi times a half, that is equal to pi over 2. So when x goes from 0 to half, then t changes from 0 to pi by 2. So let us now write this integral I in terms of t. So we have here t is equal to 0 to pi by 2, and then we have mod of x times cosine pi x. So x is t over pi, and then we have cos of t, and then dx is dt over pi. So now we can write this integral as 0 to pi over 2, and here we have mod of t over pi cos t, right? So we can take 1 over pi, that is mod of 1 over pi is simply 1 over pi, and then we have mod of t, and then we have mod of cos t, and here we have dt over pi, right? So here we have written this mod function as mod of 1 over pi, that is simply 1 over pi, and mod of t times mod of cosine t. Now 1 over pi and 1 over pi is 1 over pi square, and taking 1 over pi square outside the integral, then we have 0 to pi by 2, and here we have mod of t, and then we have mod of cos of t, and here we have dt. So now when t varies from 0 to pi by 2, right? Since t is a real number and all the numbers from 0 to pi by 2 are positive, right? So mod of t is equal to positive t whenever t is greater than 0, and here t belongs to the interval that is from 0 to pi by 2. Hence all the t's are positive, so mod of t can be easily replaced by positive t, right? And here we have a mod of cos of t, right? And mod of cos of t can be written with the help of this definition. So we can now write mod of cosine t as positive cos t whenever cos of t is greater than 0, right? And see here t belongs to the interval that is 0 to pi by 2. So we are in the first quadrant, right? That is from 0 to pi by 2. And when we are in the first quadrant, then the cosine function, that is cos of t, is positive, and positive implies that cos of t is greater than 0. So mod of cosine t can be written as that is positive cosine t when cos of t is greater than 0, and when t belongs to this interval that is in the first quadrant, then the cosine function is positive, right? So we can now write 1 over pi square. Here we have 0 to pi by 2. Mod of t is positive t, and mod of cosine t is positive cos of t, and here we have dt. So now we have 1 over pi square 0 to pi by 2, and we have t times cos of t and dt. Now here we can see that this is the product of two functions of t, right? So this function is a polynomial function and this is a trigonometric function, right? So now we can write the integral I as 1 over pi square, and we have 0 to pi by 2, and here we have t cosine t dt. So we can now write t and then cos of t dt. Now see the derivative of sine t is equal to cosine t, right? So we can write the derivative, that is d sine t is equal to cos of t and dt. So we can replace cos of t dt by d sine t. So here we have d sine t, so that we can now apply the formula of integration by parts. So now we can take this function as u and this function as v, right? So using integral u dv is equal to uv minus integral v du, we can now write 1 over pi square, and then we have u times v. So u is t and v is sine t, right? So we have t sine t, and then we have the integral, that is v du. So v is sine t and du is dt, and the limits of integration are from 0 to pi by 2. So now we can write 1 over pi square, and then we have t sine t minus the integral of sine t is minus cos of t, and the limits of integration are from 0 to pi by 2. So we have 1 over pi square, and then we have t sine t plus cosine t, and limits are from 0 to pi by 2. So now let us substitute the limits and we'll take the difference. So we have 1 over pi square, and then first we have here t is equal to pi by 2, then we have sine pi by 2, then we have cos pi by 2. So first we have here t is equal to pi by 2, and then we substitute t is equal to 0. Then here we have 0 times sine 0, and then cos of 0, right? Okay, now let us simplify it. So 1 over pi square, and here we have sine pi by 2 is 1. So we have pi by 2 times 1, and cos pi by 2 is 0. And here this term is 0, sine 0 is 0, and then we have cos 0 is 1. So now we have 1 over pi square, and here we have simply pi over 2, and here we have simply minus 1, right? Okay, so now multiplying these two terms by 1 over pi square, we have simply 1 over 2 pi, and here we have minus 1 over pi square, right? So viewers, the value of this integral is equal to 1 over 2 pi minus 1 over pi square.